And I believe example one is a very good start, and it gives us a few interesting examples of taking care of various integrals. So first of all, I need to, I guess, recall the interesting formula that deals with the antiderivatives. We saw this formula before. They put it down such a way it's du divided by u squared plus a squared, or a squared plus u squared. Maybe I'll write it as u squared plus a squared so we could see better the resemblance of this formula with our example. So this is arctangent. The antiderivative, according to the tables, is arctangent, and it's actually having a in denominator in front of this arctangent. And arctangent we take of u over a. And what's good to realize here is that a is a constant. A is going to be constant. So let raise some number. And u is a function of variable, let's say x. So variable is here, it's x. And that's why I could use my formula for part one of this interesting example. It's nice because it's right away giving you the answer. So instead of u, I put letter x. Instead of a, I put number 3. So it will end up being, so I'll write example 1 part A. So the answer will be 1 over 3, right? What's important is to write down it carefully. Also, there is a 4 that we can factor out the integral sign, right? It's always like that. So we end up with 1 over 3 times arctangent. And for the argument of function arctangent, I have a fraction with same denominator 3. And instead of letter u, now we have x. So it's so-called table integral. It's pure table integral, and it looks like that's exactly what they have here. So the point is carefully match coefficients, because I know that sometimes people forget 4 or is not sure what this 9 is, so that's the use of 4. Now, for part B, it's a pure substitution, because when you take derivative of x squared, it's 2x. So the substitution will be here of your denominator. So whenever you have a denominator, your goal is going to use that denominator to substitute, right? So you use letter u. So I take derivative of x squared, which becomes 2x, and I attach dx to it, and that will be du. And now I see what's going on in the actual numerator of my integrand, and I see there is 4. So it's not 2, but 4. And I can easily produce 4 if I just double both sides, right? So if I put 2 here. And that way we will end up with an integral, and my denominator becomes u, because I replace it entirely, and that's the goal of any substitution, to replace it entirely, your denominator. And the numerator turns into 2 times du, and that's my upper part that I have here. Well, that's what they have here, actually. And then you take ln, which is antiderivative of 1 over, and then instead of ln, you put x squared plus 9. Please notice they lose absolute value. Why? Well, because you could technically leave it here, but since x squared is positive, we deal with real numbers. So x squared is positive, and add 9 increases it, so we don't need absolute value bars. It's good to realize, because sometimes you do need absolute value bars, and it's not hard to put them. So I would advise you to just keep absolute values for just in case, but they show that it's not needed. Okay. So part C here. What happens if you have powers 2 or 3 or bigger? It doesn't really matter what other powers you have, but you need to divide. So you need to perform so-called long division. So the third kind of problems when you need to long divide. And how do I divide? Well, I always divide first terms, right? So I have to put 1 here, because when I multiply x squared by 1, I get that x squared. But of course, I have to continue multiplying, so it will not be just x squared, but also 9 times 1, which is just plus 9. And then I have to subtract, so then I have to put a minus, and this subtraction will actually change the sign with a remainder, right? So in other words, you're going to split this integral into 2 pieces, and one of them, I say, Alex, careful, it's x squared divided by 4x. I had to be careful. I divide by 4. Before I wrote, I just noticed that I forgot 4. Well, it's not hard to fix, so we can fix. We put 4, right? So it'll be 4x squared. It has to be the same. So these guys cancel, and 4 times 9 is not 9, is 36. Okay, 36, whatever the numbers are. We don't really care, but we want to, of course, be careful with numbers, because otherwise the answer is not going to be the same. So minus 36. Okay, so now what? Now I have the integral that I produce, and this is going to be 4, that's my quotient, plus my remainder, which is negative 36. Well, you say, Alex, why don't you just put minus? Yeah, plus and minus is minus. Well, just to be precise. So 4 is a quotient, then what remains is negative 36. So this is split into 2 pieces, into 2 fractions. One with denominator the same, and the second also with the same denominator. So I need to wake up. I think I need to say to myself, wake up, Alex, wake up, because 4 is a quotient. So 4, and that's it, right? Why do I put? But anyways, so 4 is a quotient. And then the remainder will be still divided by the denominator, which is x squared plus 9. Okay, so this way we have a split, and we could also put dx with each piece, so it will become a pair of integrals. And the first one, I'm sure you know how to take the antiderivative, right? It's just going to be 4x. And the second integral is the one that we just did. We just did in the very first part A of our example, so that minus 36 will go out and will be multiplied by exact same arctangent, right? So whenever you have larger power than 1 in your numerator, 2, 3, of course, if it's polynomial nature, so the whole numbers for the powers. So you can do long division. Then you split this into simpler integrals. And that's exactly what they did here. So you can see 1 was 4, the whole part, and minus 36, the second. So this is, I guess, a good start that makes you realize that sometimes you do substitutions, sometimes you use table, but sometimes you have to use the substitution. That's what we did in part B. And this section is actually about the substitution in here, and substitution will be an example too. I think it's a good idea to go over all of their examples because they cover lots of parts. I'm not gonna, of course, copy everything, but for instance, here we have this 4 minus x squared, that's arcsine, right? So if you are looking at the table of integrals, so if you try to take a antiderivative of du, and then you have a square root, and then we're dealing in the tables with a squared minus u squared. Then this is arcsine. So I try to justify this at the beginning of our class. I know it's already been a while, like almost a month ago. Arcsine of u over a. If a is 1, then it's just over 1, so that's just u, but over a in general. Please notice that when you take arctangent, there's 1 over a factor in front, but with arcsine, there is no such a factor in front. And again, if you want to verify why this is, remember a right triangle, so that was a little bit of a lengthy procedure. But the point of story, when you take the antiderivative of this arcsine, derivative of arcsine, it will be 1 over square root. So anyways, that's the formula they're using here. So it tells you that a is 2, right? So you will be ending up with arcsine, but now in numerator, you have a split, because when I take denominator as a substitution x squared, that will be 2x, so that will be derivative of numerator if I separate x, and then if I use another piece on the top is 3, so if I split it into 2 integrals, then the second one will go under the arcsine formula. For the second will be arcsine, but for the first it will be substitution, so it will be just some number. So you could trace whatever they did here. I think it's a good practice. If you want, I can, of course, do it for you next time. But I guess it's all in front of you. But it's a good idea to do the substitution for practice, just like we did in the previous example. So again, if you just look at it and say, oh, okay, no, you want to make sure you get a piece of paper, pen, and actually write it down, because it's seemed to be okay, but when you start to write things down, you might find out that you get stuck at one of the points, and that's the something you don't want to happen, right? You want to write it down. And the reason is that there are lots of little exercises at the end in this section where the exercises are, and those are good for practice. Now, here's a neat substitution, I think, because if you have x cubed, it's x to the power of 6, Alex, open your eyes. Well, yes, but if you substituted x cubed instead of, let's say, variable x cubed as a u. And then if you square it, then it will give you your numerator, because if you treat it as, instead of x cubed, as a u squared, something like that, so you'll end up 16 minus u squared, and that will be previous exercise, which is arcsine. So if you were to replace your x cubed as a variable u. And the reason you do it, because numerator has x squared. I say, Alex, what if my numerator was x cubed or x fourth or any other power of x, just x? It would not be an easy exercise, because with x to the power of 6, you would probably be completely stuck. So the only exercise you can do is with x cubed, turns out, substitution. Or if it be x to the power of 5 on the top, then you would replace 16 minus x to the 6, the whole radicand and derivative would be x power of 5. Because otherwise, you can't do it with this type of methods. So I'm trying to convince you there is very limited integrands that we can work with. That's the reason. When I say, so how could we take it? Well, usually the other method is split it into series, and that's what we're going to see in the chapter 9. But that's sometimes doable, sometimes it is not. So another substitution, but now we're using a little bit of a trick. So let me get some room here. Maybe, I don't want to overload you with these ideas. I just want to do maybe one more, and then we'll try the actual exercise at the end. But here's the problem we encounter, because our denominator is the only thing I can substitute. When I take a derivative of denominator, derivative of e to the power of x is the same e to the power of x. So I need it on the top. That's the point. When I try to do my substitution again, I must have e to the x on the top. And that's why we do the cheap trick. We add the same thing, and then we subtract that e to the x. And we add e to the x so that we'll split into two pieces. So first two terms of my numerator that will cancel nicely with denominator, so it'll be just 1. And that one straightforward to find the antiderivative. And the second piece is going under the substitution. So for the second piece, when I substitute my denominator, see, that's probably worth to write down. So that's another u. And the derivative of that will still be e to the x, because derivative of e to the power of x is the same thing. Well, 1 will disappear though. So this is going to be du. And that's why my second integral will become much nicer, because when I substitute denominator with u, and my entire numerator will become du, that's where ln will come out, right? Because when you integrate du over u, it's ln, and whatever argument is they put together. See, they already at the level where they don't need to write it as du over u, so they skip that step. Do you have to skip that step? Well, eventually you will, after you do a few substitutions. If you keep doing substitution 2, 3, 4 times, then you say, oh, yeah, I don't need to do it. I'll just write it down right away. So maybe if you have a tutor, the tutor will impress you by skipping a few steps. But, well, your tutor already done so many exercises, so there's no need to, I guess, write them all down. But I would highly recommend that you actually write it. So let me try analogous exercises. I think it'd be a good idea then to try analogous exercises. Since we're doing e to the power of x stuff, I can right away look at 35, try 35. Because e to the 11x, that's just 11 will go to denominator. So there is no substitution really needed, but it's still good to write it out, make sure that you have the same coefficients, right? And the goal is to make sure it's correct. So it's a good idea to always check it out with the back of the textbook. So anyways, I'm going to say, Alex, there is either the negative x. Yes. Please notice that I want to write it with something in numerator, and that's why I'm going to do the algebra. I'm going to try to produce the same denominator here. So I'm going to turn this into e to the x over e to the x, right? So I multiply e to the x and I divide by e to the x, so e to the x will cancel and will give me just 1, so these two cancel. So why I do this is because on the top it'd be 2, but on the bottom we'll have complex fractions. So e to the x will be in denominator, but my numerator is going to be 1 plus e to the x. So I'm dividing by that fraction, means I'm taking a 2 and multiplying it by a reciprocal. Right? We always can flip our denominator and multiply and produce this type of integrand. So now when I start to integrate, I could put integral, I just don't want to copy it. So the 2 will go in front, e to the power of x, right? And then we have that denominator that I will substitute. See, it's a little bit of writing before you can do it. And again, as I said, some tutors may visualize it right away, which is good and impressive if they do it without a mistake, of course. Because if you're not sure if you can possibly make a mistake doing all this algebraic manipulation, so just write them down. That way you save yourself from making mistakes. So if that's you, then the derivative of e to the x will be the same thing, with dx will be du, right? So this is how I start, and that will enable me to clearly see what is going on, right? So I can now replace my entire denominator with a u, and this numerator part is du, so we get ln. It's actually going to be 2 multiplied by ln. So the question is, don't forget your absolute values, right? And say, Alex, they did not need it in that exercise. Yes, in that exercise, remember, they didn't need it, but now look at what argument of ln you have. Your substitution, right? 1 plus e to the power of x. Is that always positive? If so, then you can use parentheses. If not, then you use absolute values. So I would, again, recommend you use absolute values, but e to the power of x is always positive. So you add with 1, it is still positive. So you don't technically need the absolute value. But again, nobody will punish you if you still have it. In fact, I think it's good. It shows instructor or grader that you actually aware of absolute values, domain of function e to the x, which is nice. And again, what's important is to realize that whenever you have e to the power of x, you need to take its derivative, and it's the same thing. Like exercise 46. Since I started to deal with e to the power of x arguments, I'm going to beat them to death. So I'm trying to make sure we take care of all of them. So looks like here it's not e to the x. It's e to the power of 1 over t. I say it doesn't matter. Well, it does. So substitute. So 1 over t, or t to the negative first, and then when you take a derivative, it will be negative 1 over t to the second. And that's great because at this stage, I can see that I have that t squared is just what I need to see in my denominator. You see that? I just don't have a minus sign. And we know it's constant, it's a negative 1 or something, so we don't really care much for that. So what I can do is just negate both sides of my equation. So I multiply by minus 1. So this is going to take minus out, and I'm going to end up with something extremely nice. So instead of e, will be raised instead of 1 over t to just u. So what is this? What kind of thing? Is that b, Alex? No, it is e. Practice to write unknown e a little bit better. I need to be careful. So it's e to the power of u. That's my numerator now, right? So I'm doing the exercise 46. So e to the power of u, and then t squared with dt will end up being du, but with minus sign, minus du, or I can take out minus. And then we're done, right? So e to the power of u is the same thing. When you take antiderivative, and instead of u, I put back my variable. I start with 1 over t, and then plus the constant. So again, I'm doing it slowly to make sure I don't skip any steps, to make sure that everybody is agreed that we're doing the right thing, right? So analogously will be with tangents, so that's now you see the parentheses. So the goal is usually to replace parentheses with substitution or denominator. So here are two possibilities for substitution. So for parentheses, looks like it works because 2 here is in denominator. So if you take derivative, it'll be already the same thing. So t squared on the bottom, and that'd be what I have. So it'd be tangent of 2 over t. So it'd be 2 over, maybe I'll write it out. Maybe I should do it here separately. Why not? Because that's already a new function, tangent. So now we're gonna move to some of trig examples. See, these problems you can do forever and just practice, and eventually you say to yourself, why do I need all that? I already know how to do all of them. And that's my goal. Make sure you feel comfortable in doing all of them. Miss Alex, I have to do all of them? Well, we're going to have a midterm in a couple of weeks. So for the midterm, I'll really point you out what exercises I'm going to ask you. So you won't have to do all of them. You'll just say, oh, okay, 45, so you know you're going to get tangent, something like that. So that'd be more straightforward. But the goal is you try, if you plan to do more math in the future, and I'm talking about differential equations, we'll be very heavily using this trig antiderivatives. That'd be the one. If you're going for that, you would be highly recommended by me to do more exercises. But if you don't take any more math, that's fine. You just do a couple of problems, you get your perfect grade. I'm sure you're going to get a very good grade on this class, and because I give you a chance to fix things, so no worries, it will be good. So tangent of 2 over t, right? That's what I substitute as my new variable. So I want to integrate tangent of u. That's the point, because that will be in the formula, in the table. So how about derivative of that? Where we already done 2 exercises with it, so we know that minus comes out, and then t squared, right, will be on the bottom. And again, it's worth to actually differentiate and use the formula for power rule for derivatives and make sure that you do get the same thing. Otherwise, ask me, we'll work it out. So we don't have the 2, we don't have negative, so I need to take care of these constants. And this is again standard. So if you don't have negative 2, well, then just put it in denominator so it cancels, right? So you're going to end up with du over negative 2 or minus 1/2 in front of your result. So we don't really care what the constants are, we just take them off. So now, how do I integrate tangent? It's also substitution, sine over cosine. So you substitute as usual denominator. So you pretty much never substitute your numerator unless you cannot do the substitution for your denominator. But that's a good thing that we can, because derivative of cosine is negative sine, right? So if I replace cosine of u, like say do 2 substitutions, it doesn't matter how many substitutions you do, you will always return back to the original variable anyway. So cosine is going to be your substitution, and derivative of cosine is negative sine. And again, that's something you need to know, or write it down, and where you can see that. Remember, beginning of the textbook, those pages with the formulas, with a little table of formulas. So that'd be your pages. Make a picture of that, or just remember where to find. So anyways, now I have negative sign again. You say, oh, negative sign, I already know what to do. So just divide by -1 both sides, right? So that way you have exactly sine of u du. And that stuff you will replace with dz over -1. Let me get another color. It's kind of hard to see. The black. Dz over -1. And notice that -1 now will cancel with what you have in front. But don't hurry. So, and then also you have what? So you replace that with numerator, that's dz, and cosine is still there in denominator. So you can put, instead of cosine, it's letter c. And it's multiplied, so better put in the parentheses. And then integral and -1/2. So if you write it out carefully once, then you probably won't need to do it again. So anyways, 2 minuses give us plus, so we just left with positive 1/2. When you took the antiderivative, you end up with ln, right, of letter z, and now I'm gonna little by little return back to original variable. And that will be done in 2 steps. So first of all, I need to take, instead of z, and put what I used to substitute, so cosine. Please notice cosine may be positive or may be negative. So I need to keep that original absolute value. And then I need to also replace back my variable u. So I put 2z, 2 over t, sorry, 2 over t here. I don't want to copy because of that, but the point is you want to give them the answer with original variable, 2 over t. So it's not hard, but it's a lot to remember. That's why I highly recommend that you write it down. So it's going a little by little, and we can try another exercise. Now, for a change, I can get something else, something, let's say, with trigonometry. We just did one with tangent. Maybe I can do another one with tangent, like number 38. So at this stage, you could just take a little look at the exercise. Maybe I'll do 38 and then go back to those examples they provide me with, so I could see other strategies, because when you do substitution, there are lots of algebraic strategies that bring you to it. And we just saw some of them with e to the power of x, such as adding, subtracting stuff, the same stuff, or there's another one like multiplying numerator and denominator by the same thing to help us out with split of integrals. And it's nice, the straightforward one, maybe I do them because I spent already lots of times doing this procedure, but you can also check out and see how you will do this. So anyways, what is this? What kind of structure we have here? Ln of cosine, so what kind of thing it is? Well, first of all, if you see tangent and such a stuff as ln cosine, you better write your tangent as a sine over cosine, right? So that's probably a good start. Sometimes yes, sometimes not. Again, depends on the level of exercise. So sine over cosine of x. And then there's ln cosine. So why they put that ln cosine? So that's probably for the reason, right? And dx. So you probably want to take the derivative or antiderivative or something like that in here. And turns out the good idea is to substitute. So one substitution of cosine, but I would recommend that you look at the ln, because ln is usually the problem, because ln is something we can differentiate, but we will have hard time integrating. That's why advice is try to start here with ln and see if you can possibly do the substitution with that nasty looking stuff as new variable letter u. And then I hope your derivative will be sine over cosine, which is tangent. If not, well, then we're in trouble. So let's take derivative of ln, and it's 1 over and 1 over argument, which is cosine of x. That's first part. So we need to do the chain rule. So now I forget ln, take derivative of cosine, which is negative sine, right? And you say, Alex, yes, that's exactly what I have remaining, but with no minus, and that's fine. That means that minus will be with over du, right? So instead of ln cosine, I put du with minus in front, right? And sine over cosine, oh, sorry, ln of, got carried away. Let me get rid of it. My derivative, sine over cosine, is du, right? Not hurry. So this part and that part is my negative du. And it is multiplied by ln of cosine, which is u. So this stuff is u multiplied by negative du, so minus stays, and u squared over 2 is my antiderivative. So it turns out when, in general, when you have your argument nasty looking, some unusual ln cosine, it means the problem is not hard. It means you just take the nasty part and replace it with new substitution, you'll be done. So now I need to go back to my original variable. So instead of letter u, I'll put that ln cosine. Whatever, we don't care, we just copy it. And this has to be squared. And then it has to be divided by 2 and plus the constant. So this is my answer. It's not hard. So as promised, I will return back and look at what they have left here in the section. So trig identity, example 6, secant squared minus 1 instead of tangent. And when you know how to integrate secant squared, which is tangent, you get the answer right away. So tangent squared is not in the tables, but you can replace it with trig identity secant squared minus 1. So last time we saw this formula, it's so-called Pythagorean theorem. That's worth to think of it because very often you will encounter this formula. So that's trig identities and, oh, ln sine, ln cosine, so they actually did substitution like I did in that problem 38. So is there anything else here? And that's something we did already. So here's the part of the table that we're using in this particular section. So it looks like it's nicely provided here as well. So let's see, that's a lot of formulas, Alex. Well, first, once you know the power rule for the 5, which is ln e to the u. So those are ones that you're already very familiar with, I hope. If not, well, look at it, and the more often you look at it, the better you feel about it. You don't have to memorize. You can just have it somewhere where you can easily access, right? So just keep it someplace. But eventually you will see that you really need to know antiderivative tangent, we just did today. So what is this coming up? Not sure. So secant cosecant ln of some, and then secant cosecant squared is tangent, and that's the one we just saw in example 6. And then secant tangent, that's the one we didn't use yet, we will. And then there is a arcsine and arctangent. One interesting observation. Please notice just arcsine, arctangent, and arcsecant come out. One can say, what about arccosine, Alex, or arcotangent, or arccosine? Well, we never use those. Turns out arcsine you can also write as arcsine, arccosine. But since Pythagorean identity is sine squared plus cosine squared equal to 1, so you can technically convert it to arccosine. But there is no need. That's why there will be never arccosine. And same with arctangent, because tangent is 1 over cotangent. So we always use just arctangent. Don't worry about arcotangent. But technically, again, you could rewrite it using some trig identities. And yes, that's pretty much all this section is talking about. So there is another thing, I'll probably do it next time. I need to get a problem. I believe it's in the next section. There'll be completing the squares. I know there's procedure that people that take my college algebra classes really don't like to complete the square. And sometimes it is very important, like in this particular situation. I think other than that, there's some algebraic tricks that we will be utilizing anyway. So I think at this stage it's a good idea to stop with this whole story. Thank you for handling all that. So we'll practice more. So, and then maybe next week we'll have a little quiz like exercise. Remember, we had a quiz last week. So now we're going to accumulate a little bit more material. So I'll find something very short and neat for you for the quiz where you have to think about it. And then we'll have a little quiz next, maybe Tuesday. So that will be the plan. And if you don't have questions, I'm going to stop this recording and enjoy the rest of the day and have a good weekend. Bye-bye.